Okay, so today we are going to look at exercise 33.1. This is topic carboxylic acid. The first question that we are going to look at is question 5. If you have your notes in front of you, that would be very helpful. Okay, let's start. The following route shows how a carboxylic acid, so you can see COOH, can be converted into amine. Okay, so during this conversion, your COOH will be converted into a COCl, which is an acyl chloride. I hope you can see that. And then CONH2 is an amide. All right, if you cannot identify the functional group just by looking at the structural formula, then I suggest you to draw it out. Suggest a reagent for step 3. Okay, so for reagent for step 3, you don't have to worry about that now because that will be covered in the next topic, and that is called the reduction of amides. Okay, so we'll skip that. The second part, angelic acid C5H8O2 is a natural product isolated from the roots of the angelica plant. Angelic acid reacts with hydrogen plus nickel to form T. So that means if you use hydrogen that looks like a hydrogenation process, you are adding hydrogen to a unsaturated bond. That means there's a double bond somewhere, okay? T undergoes the above synthetic route, so T follows the same route. U can also be made by reacting 1-bromo-2-methylbutane with ammonia. Both angelic acid and T exist as stereoisomers. Okay, so to do this, I would have a fresh page, okay, just to give me an idea. But if you have space at the bottom of the paper, that's fine as well. Okay, so let's see. The structure of angelic acid, the name acid suggests that the structure would have a COOH, and even from the formula, I can already tell there's 2 oxygen, okay? And there are 5 carbon, 1, 2, 3, 4, 5. Now, bear in mind, with this kind of questions, it's like a trial and error, okay? So that's why you don't put down the structure of angelic acid in the box yet, because I know that's not the structure, okay? Let's have a look at the formula again. C5, so this is the angelic acid. I'll just call it an angelic acid. C5H8. So if you count the number of hydrogen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's more there's more hydrogen than what is stated in the formula. So my guess is there is a double bond somewhere. Okay, so this is still my proposed structure of angelic acid. I don't know it yet. With hydrogen, okay, with hydrogen and nickel, it forms C5H10O2. So that looks to me, the double bond has been broken. If you count the number of hydrogen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So it matches with the formula of T, which is C5H10O2. T undergoes the above synthetic route to form the amine U. So that means if we look at the route above, you start from a carboxylic acid, ethanoic acid, to form an ethylamine. You form an amine, right? So I label this T, we go down the route, and I should expect to see something that looks like this. All right, starting from acid to amine, referring to this route, this whole thing. Okay, so I just want to look at the starting and the end. So you can see that the COOH has now turned into an NH2, okay, maintaining the number of carbons. Are we all okay so far? Okay, so my amine is now amine U. I'll just label that. You don't need the structures to be big because I can assure you that I will erase this whole thing again later on. Okay. U can also be made. So I'm going to use a different color. Reacting 1-bromo 2-methyl-butane. So that's butane, 4 carbon. That's carbon number 1. There's a bromine. Carbon number 2, there's a methyl group. Okay. React with ammonia. I form structure U. Okay. I also form a structure U from the green root, which I have no idea how the structure looks like. I'm just making up. I am simply putting the double bond in at a random place. But the third point, the reaction in red, is definitely I know the structure because they tell me the starting material and then they tell me the product. If you remember from your AS syllabus, ammonia reacting with a halogenoalkane in a nucleophilic substitution reaction. Can you still remember that? So what happens? The bromine is substituted with the NH3 group, but be careful. So I'm just going to maintain, keep everything, and the only changes is made here, NH2. Okay, so the bromine on carbon 1 has been substituted. All right, so this structure U is something that I am confident with. All right, because the question tells me what we started with. So that means there's something wrong with my structure, Sinikan. My structure Uani is wrong. So I need to change that. I need to modify it. Okay? So my structure U is now, I'm going to flip it because I've got my NH2 on this side. So what I'm going to do is just flip my structure U and to work in reverse. Based on the structure U, I will work my way to the start. Okay, because I didn't know this structure, and this structure, even this structure was wrong, as you can see. Okay, so let's see. When drawing this, you have to make it a habit to number them so you don't drop any, you don't suddenly change the structure. Okay, so 1, 2, 3, 4, and at carbon number 2, there is a methyl group. And this is now my confirmed structure of U. Are we all okay? This reaction, I will just mention, this is a nucleophilic substitution of halogenoalkane. And this is your AS stuff. Okay, if you want to look back. Okay, I'll let you copy this part first, and then we will work our way back to the starting material, okay, because that's easier. Okay, right, so we trace back our U to structure T, okay? So the T, so I'm just going to draw the arrow up, to show that we're working in reverse. Okay, our T contains COOH, and that COOH is, if you look at this structure like, yeah, that COOH will have to go through 3 steps to be converted to NH2. Okay, but we know that it can be done. That NH2 must have come from the COOH. So if we want to go back to the structure of T, that means this NH2 group came from COOH. So what do? We just maintain everything, same thing, keeping the number of carbon the same, but we change the functional group of NH2 to COOH because according to the question, structure T ada COOH functional group, right? So we keep the same position, 1, 2, 3, 4. Don't forget at carbon number 2, there is the CH3 group. And that is structure T. How do I know this NH2 can come from COOH? You refer to this root. COOH goes to NH2. And in the question, they say T undergoes the above synthetic route to form U. So that means T, having a COOH group, can undergo through the 3 steps to form U, which has the amine group. Okay, so this kind of question needs a lot of practice, really. So that means my proposed structure of T was wrong. Okay, but my functional group is correct. I've got the COOH. It's just that instead of having a straight chain, I've got a branching on carbon number 2. Then we go back to angelic acid. We want to go back to angelic acid. Maybe I move it. It's okay. I'll just do the overlap. Okay, so from T, I want to go back to angelic acid. Obviously, my angelic acid structure here is wrong. Okay, now can you see what I have on angelic acid? I have COOH, which is already correct in the right place of my T. The double bond. I need to place my double bond based on structure T, but the question is it between 1 and 2? Is it between 2 and 3? Or is it between 3 and 4? I can't just say, oh, I'm going to randomly put it, I don't know, 3 and 4, 2 and 3. We need to go back to the question again. Both angelic acid and T exist as stereoisomers. So stereoisomers, there are 2 types. Can you remember the stereoisomers, the types of stereoisomers? Cis trans and what's the other one? Optical, good. So angelic acid, we already said it must have contained a double bond. So it must have a cis trans because cis trans is for double bond. Cis trans, okay? Now, before I draw angelic acid with a double bond, I just want to check with you. Can I put my double bond here? How many bonds will carbon have? 5, okay? Can I put my double bond here? Will I have a cis trans? The requirement for cis trans is each carbon on the double bond is attached to 2 different groups. So can I have cis trans if I have a double bond here? Some yes, some no. Let's check 3 and 4, okay? So 3 and 4, there's a hydrogen and a carbon here, and there's 2 hydrogen. Can I have a cis trans in 3 and 4? No. So I go back to 2 and 3, okay? So if you look at 2 and 3, this carbon is attached to a CH3 group and a hydrogen. Okay, well, I'll show you. Okay, so we concluded that in the angelic acid, bringing Like the structure of T, do not lose anything. That's why numbering is important. So I number them COOH 1, 2, 3, 4. Okay, so 1, 2, 3, 4, and there is a CH3 group. And just now we said the double bond is between carbon 2 and carbon 3. So if you look at, if I just draw out the hydrogen, so you can see, right, carbon 3 is attached to a hydrogen and a CH3 group. Carbon 2 is attached to a hydrogen and this whole COOH. So they can have cis trans. Whereas 3, 4, no cis trans. 1, 2, you cannot place a double bond there because the carbon would have 5 bonds. Okay, so I will let you copy that down. Because of this, cis trans is possible. Okay, so I'll zoom that out for you and let you copy and digest that information. If you have any question that is not clear, please ask now. Yes? Apa? Ah, yes, you're right. There's no H. That is right. There is no H. Sorry. Sorry about that. Okay. Thank you for pointing that out. That carbon number 2 is attached to COOH and CH3. Yeah. Okay. That was a mistake. But still can have cis trans. Right? Thank you for pointing that out. I'll zoom it out. Can you see? Is it okay at this size? Well, that's the best I can do. So then we can answer the question. Suggest structures for angelic acid. They don't specify the structural formula or any particular formula. So you can choose whichever formula you want, making sure that the structure is correct. Okay, if you need to number them, will they allow you numbering the carbon? I suppose it's not wrong. Okay. But make sure it's a complete full formula, okay? Kalau you want to draw displayed formula, you must make sure you include the hydrogen. Don't draw the structure. The structure is incomplete. You have to fully draw the hydrogen like there's a CH3 here, okay? In the marking scheme, they draw it as, I believe they like to draw skeletal formula, okay? But if you are not a fan of skeletal formula, that's fine. Just make sure, maybe I use a different color, blue. Okay, so angelic acid is CH3, CH with a double bond, C, CH3, COOH. Or you can always draw the structure, no problem. Um, 1, 2, 3, 4, OH. 1, 2, 3, 4. So there's a methyl group down there, and the double bond is between carbon 2 and carbon 3. Okay, that's the answer in the mark scheme as a skeletal formula. So I'll just leave it there. And then the next structure is T. We follow the structure of T in red. The green one I've already cancelled out. Make sure you do not answer. You don't follow the structure in green color. So kalau T, it will be, see, again, 1, 2, 3, 4, 1, 2, 3, 2, 3, 4, and then there's a OH, 1, 2, 3, 4. Don't forget on carbon number 2, there's a methyl group, okay? And for U is also, but this time ada NH2. So 1, 2, 3, 4. And be careful, you must count 1, 2, 3, 4, NH2. And on carbon number 2, there's a methyl group. So don't do this, because that only has 1, 2, 3 carbons, and that is wrong, right? So numbering your carbon is beneficial. You will not lose anything if you number your carbons. If you think that will slow you down, but at least it will make sure you get the right structure. Okay. Okay. Next question. What time do we finish today? 10? 15? 20? Okay. All right. Just remind me. Next question. Question 8C. I'll let you have a read at question 8C. So that's the table. This one, Dana. Okay, I'll move on. Question C. If you need, you can draw out the structure. C double bond O CH3 COOH. And then you've got a diethanoic acid. Okay. The functional group were more or less the same functional group. This one got COOH. This one got a ketone, COC. That's a ketone. And also it's got a COOH. And this one got COOH. 3 tests were carried out on separate samples of the organic acids shown in the table. The following results were obtained. Tick means observed change. Cross means no observable change. Okay? So in a way, tick means there's a reaction. Cross means no reaction. So your task in the exam is to find a reaction that will, so if we're looking at the first part, the reaction only reacts with methanoic acid, but does not react with the second acid and the third one, the dioic acid. Okay? Before we start, there's something that you need to realize. We have a methanoic acid and diethanoic acid. What's so special about these two acids? Or ethane dioic. These two acids are special because they have the only property that is owned by these two members of the carboxylic acid that does not belong to other carboxylic acids. What is it? Sorry? Yes, these two can be further oxidized. So we're going to use that information. Can be oxidized, but other carboxylic acids cannot be oxidized. Okay? Okay. So reaction 1 is a little bit difficult because that reagent only reacts with methanoic acid, but it doesn't react with this ketone plus acid and just dioic acid. Okay, so I'll move on to part 2. I think part 2 is easier. Okay, so what does, so in part 2, you can see that the middle acid gives a positive reaction. That means it reacts with that reagent, but it doesn't react with the other two. Okay, so looking at the functional group, what does the middle acid have that the other two don't? Ketone. Okay, so that means this reagent will only react with ketone. Only reacts with ketone. You may ask, well, how do I know that? Because if it reacts with carboxylic acid, then all 3 will have a positive result. All 3 will be ticked. Okay? Does anyone remember a test for ketone or a reagent that will only react with ketone? Yes. 2,4-DNPH. Do you remember that? Okay. So the answer is 2,4-DNPH, reagents and conditions. Actually, I don't remember if there is any condition for this. I assume that it would occur at room temperature. Now, what do you observe when 2,4-DNPH reacts with ketone? Sorry? Yes, correct. Good. It's orange precipitate. Okay, good. So reaction 2 is the easiest, right? So this is the kind of apa, hack or technique that I want you to do in the exam. If you cannot answer test 1, skip it. Okay, as long as it's not related lah. So now we move on to test 3. So this time, test 3 only reacts with methanol and dioic acid, but it doesn't react with ketone, and it doesn't react with a normal carboxylic acid. Okay, so this is what I was talking about. What makes methanoic and dioic acid special or different from the others? Okay, so I'll just add on. Test 3 only reacts with methanoic acid and dioic acid, but not normal COOH. How do I know that? Because the middle acid contains COOH. Yeah, it contains COOH, tapi it doesn't give the same reaction. So we now go to the oxidation reaction. Can you find a reagent that can oxidize both methanoic acid and ethane dioic acid? So look at your notes. What is the oxidizing agent that we can use for both methanoic acid and diethanoic acid or ethane dioic acid? There's one reagent. Yes? KMNO4, what's the reagents, conditions? Sorry, what's the condition? Warm. Does it need to be acidified? Ah, okay. So acidified or H plus. Observation. What would you observe of the potassium manganate? Color change. What color is potassium manganate? Purple. So it will be purple to colorless, or purple color will decolorize. Yeah. Okay. So now we go back to question 1. What is the reagent that will only oxidize methanoic acid, but is not strong enough to oxidize ethane dioic acid? Tollens reagent or failing solution? Good. Okay, so this reagent can only oxidize methanoic acid, but not strong enough to oxidize dioic acid. Okay, and the normal COOH will not be oxidized. This will not ever be oxidized. Okay, so which one? You can choose either one. You can choose Tollens reagent, in which case what will you observe with the Tollens reagent? Silver mirror or precipitate form? Okay, so this kind of question requires a little bit of thinking. I know in the exam, you probably wouldn't be able to remember because there are many reactions that you can think of. But hopefully with practice, okay, a lot of practice, then you should be able to answer this kind of question. All right, I Have to admit it's not easy because it requires you to have a full knowledge of all the possible reactions for all the functional groups that you have learned in A2 and AS as well. Okay, do we need to warm the Tollens reagent? Warm, okay. So don't forget that. Next question, last question before you go. I would like to look at question 9. So let's have a look at question 9. Okay, so question 9, Nani, is just a short one, but it's useful. The technique of answering this question is useful. Okay, so you see what you produced at the end and what you started with. You have a COOH. Okay, if you cannot see that, I suggest you to draw it out. No problem. COOH is a carboxylic acid. And then your product, can you see that you have a benzene with a double bond O? Yeah, that looks like, it looks to me like that part of the molecule of the end product came from COOH. Do you agree? Okay. So I am going to try to break them down, again working in reverse. I will leave some space because there's something in between. Okay. So I have a should I draw it like that? COOH. And if I break it here, I only have benzene. Okay. Another hint here is AlCl3. Halogen carrier. That is usually a catalyst for which reaction? Do you still remember? Benzene. What is the name of the mechanism? Catalyst for... What is the mechanism for the reaction of benzene? Will it attract electrophile or nucleophile? Benzene is electron rich, so it should attract electrophilic substitution. Good. So this halogen carrier, AlCl3, you need to recognize, oh, that is a catalyst for an electrophilic substitution reaction. So that means an electrophilic substitution reaction will happen somewhere. Okay, I've got a benzene already from my, after I worked back in reverse, I've got a benzene. I've got a benzoic acid, but benzoic acid is not an electrophile. I need to convert my benzoic acid into an electrophile that can attack the benzene. So that's my missing information here. Okay, AlCl3 usually works with a molecule, a compound that has chlorine. Can you think of inserting chlorine somewhere in this compound or molecule? What do you think? What do you think we can produce from carboxylic acid, the cousin of carboxylic acid? Acyl chloride. Okay, so that means this missing information would have to be the cousin or the derivative of carboxylic acid, because, well, we started from carboxylic acid. We need to convert it into something related to carboxylic acid, which is, they just want you to draw their structure. Okay, so it's just C double bond O Cl, right? And K, well, either J or K, would have to be benzene. So this is actually related to the very first topic of your A2 organic, which is arene group or benzene, what happens is that the aluminum chloride catalyst will remove the Cl, okay? Then this part becomes positive charge. This positive charge will be attacked by the benzene ring, and then the delocalization will be broken. The carbon hydrogen bond will break to restore the delocalization, and this is a type of Friedel Craft al acylation reaction. Okay. So I will leave it at that. I'll just highlight this. Why have I broken it down there? Because, well, I was looking at my starting material anyway. Okay, so for your Sunday, of course, I will give you, what did I want to give? I think 20 March. I want to give you. This is March 21. This is also March 21. March 22, March 20. I give you March 19 to do, so we can discuss. As mentioned before, I will do paper class practice every week to prepare yourself for the prelims. Okay? So we are going to discuss this together in class, but I want you to have a look at the questions first. If there's any, I believe there's a block, so please block them so that you don't have to waste your time putting them in class. Okay, I am sorting that out now. Okay, do you want to grab one set before we go?